Welcome back, guys. I'm back. It's been a while. Let's see what we were doing the last time we checked in. I guess we managed to finish the block, write and read functions. But overall, what we were trying to do is that finish the block layer and get to the virtual file system layer so that file system operations can work. But we last time managed to finish the block write and block read that I can see, and I do have some to dos here saying that we need to group those read and writes into bit more high level API, and also try batching because currently we have to wait for the request. Maybe we just send the request and either poll or probably implement the interrupt because which iOS supports interrupting. So if we place a request, the actual which IO will trigger an interrupt when the actual thing is when the actual operation is done, which can be more asynchronous instead of polling like a busy wait. So we have some stuff to do. So overall, just a quick recap of what we are doing is that I'm trying to write my own kernel, and so far I have managed to finish the scheduler, a little bit of scheduler and a little bit of memory management. We do have the virtual separation of kernel virtual address. Other than that, we do have I guess that's it. We have the MMU, we have the scheduler, and currently we are working on the file system layer. And for the file system layer, we wanted to implement the block layer so we can abstract away the things that are specific to drivers. So the high level VFS can just call block read and block write. That's the whole point. You just simply have to read blocks and write blocks. That's it. It should not care about what's inside it or what other drivers are internally working. The high level VFS has nothing to know about the internal implementation. It simply has to call block read and block write, and that's how we ended up last time. We were able to get this example working. So we have a data that is a, and we are trying to write it to the 1000th block and read from the 1000th block. So let's run it and see where we are. Hopefully it works. Okay, it does work because it has F665, which is A. We can try something. Let's see. What we can try is, where's my fucking, maybe we can try B. Yeah, let's try. And if we run it, yeah, we have 66 there in that location. So it is working as expected. It is able to write everything properly, but one of the limitation is that currently we can only make two requests. First needs to be write and the second needs to be a read, and all those index within eval and the block are static and make this process dynamic. Yeah, I guess that's what I was trying to say. If we go to our driver.c, we are using indices within the event chain, because as you let me just give you a recap. So how which IO works is that which IO has physical registers, and we have for different buffers, and for every buffer we update a virtual address, a physical address, and then within the physical address we actually write the data. And we have three different things to write to. One is the virtual descriptor, and the avail ring, and the used ring. So within the descriptor queue, we actually can write as many as which queue descriptors. And currently in this example, for a read operation, we have three descriptors allocated. And because it's like a linked list kind of thing, we have to have indices, and everything should be chained together. And within the used ring, we actually give the first descriptor's address, first descriptor's index. That's why we need the index. So in our case, the index starts from 4, and it will be 5, and it will be 6. And that's what we put into the avail ring. Where is it? I think, yeah, it must be here. We have the avail flags, and avail ring, avail index. Okay, I'm not sure. We created 3 indices. Okay. I just remembered, because so how it is how it is currently working is that because it's like a buffer, we are just calculating the index within that buffer as a memory address. So what I'm doing here is that I'm getting the size of the descriptor into the index value. So it will be the, so if the index value was if the descriptor was like 10 bytes, the first index would be 0 to 10, and then the second index would be 11 to 20, and the third index would be 21 to something. So that's what I'm calculating here, and I'll be directly using the address here, and I'll be directly writing to the fourth size, and that should just be fine. And that's what I'm doing here. And rest of the stuff we have already discussed most of it in the last attempt. It's just the first descriptor will be the actual requests that we are making. In our case, it's our request is virtio blk in, which is write request, no, which is a read request. And the second, we give the sector, and the reserved is just 0, and we allocate it in the first descriptor. And for the second descriptor, we actually just allocate some 512 data that needs to be whatever that is read will be wrote to this buffer. So we also have to mark this as writable. And finally, the third one is just saying that we have, what is it? We have to give them a status buffer, and so the which I can update this buffer when the actual operation is over. So here we have a while loop. This while loop will just keep on rotating over the current index. Whenever the current index has been updated inside the used descriptor, that means as one operation has been over. and we take the length of that buffer to confirm how many bytes we actually wrote. Nothing much. So currently our to-do was to make this entire thing dynamic, because currently it's not dynamic. So let's think about it. So we have a block reads which starts at I is 4, and we have a block writes which starts at, what does it start? Block write starts at 0, and we use 3 space for it. For a single request we need 3 indices, and our total size of which queue descriptor is just 12, so we can only make a maximum of 4 requests at a time. So we need a high level helper that is going to keep track of all the requests, and if someone tries to make a new request when all the 4 requests are filled, what do we do? Do we just put them on a while loop wait, or what can we do? Or maybe we can increase this dynamically. I'm not sure. How can we design this? First of all, maybe we need to confirm how exactly Linux does it, so that we have an understanding of what it is that is our baseline that we have implemented, and what is it that Linux implements, and we find the difference and see how we can bridge the gap, so we can actually implement something that is already in production. Instead of, I mean, we can come up with our own ideas, but still we are trying to learn how things actually work in a kernel by writing our own kernel. So yeah, let's implement something that's already working. But if I were to do it, I'm thinking about it, I just feel like maybe we could have a upper limit of let's say 250 requests, and then rest of the requests are put to wait until something else is cleaned up. But this to work will also need asynchronous, because if we can't simply put everyone to wait, because if we do that, it's simply too much people just waiting for nothing. But at least if we make that async, they can go back and do something else. So we'll have to think. Let's see. Let's write it down first of all. If we write it down, we'll get an understanding of what we want. So currently our descriptor, which queue descriptor is up to 12 in 12 size. Single request read or write needs like 3 descriptors. So in parallel we can only support 4 requests at a time. So what do we want now? Do we want to support more requests in parallel? mean, it is possible. If we want, we can increase the total size, or we just, or can we just make the other requests to wait until something is freed up. Maybe lots of threads will be waiting. What else do we have to think about here? And which IO, which queue supports batching? So as long as we have the memory, it is not an issue in the back end. So maybe we could just simply increment all of those values to, let's say, 250. No, that will be too much. Let's just increment it to 25. No, 20. Let's make it even. Let's make it 24. So there can be 24 requests in parallel, and rest of them just have to wait until something frees up. So if this needs to work properly, we also need syncing mechanism, some sort of mutex lock, and that is not yet something we support currently. We just make sure if there's a global variable, there's only one person accessing it, just purely abstract way. We don't have any mechanism to check that in runtime. Because we are a proper kernel, I think we have to support that. Maybe we can, I don't want to drift off this path. Maybe we could just simply say that we need to write this in future to make this friendly, but just write the things around it except for the waiting block. Yeah, let's not get drifted away. We might need some day structure to implement blocking syncing mechanism. Yeah, other than that, I don't see anything else. Let's just start with it. Let's just increment the total by 24. Let's define that. Define which queue max requests. Let's put it at 24, and we can change these. Which queue max requests. Let's copy that. Fucking hell. Oh shit. Which queue max request? Which queue max request? And this is also which queue max request. Okay. If we just increase the max request, does anything break? Let's confirm that. Nothing should break. Yeah, it's all working. So what else? Now we have up to 8 requests in parallel, and what do we have to change? I think there isn't anything to be changed in this function. For the read and write block, we need a even more higher helper. Because someone has to keep track of it. If someone has to keep track of it, that means I need a data structure that is allocated and it has the current number of requests. So let me define it here with kmalloc. And it's just going to be a simple structs. It's going to have all sort of metadata that are needed for getting this working. So what are the things do we need? Let's just write it down. We need a global count, and then we need a global count because every time we read and block write, we read this counter value and then figure out the index within the descriptors and within the used and stuff. Okay, I think it would be even simpler if we have a count and all the used indices so that we can remove the indices from it. And we don't have a hash map, and currently we only can have up to 24. So let's just put a static buffer of 24 requests and just assign them as already being used. Buffer used requests used requests info. Okay, what else do I need? I need a global count and I need to set which indices are used. What else? Global count, used request info. Do we need anything else? Let's say I'm inside a read operation now. If I'm inside the read operation currently, I just need one thing, I guess. Yes, I just need this information, the current index that I can use. What else? I might also need this information because inside the avail ring, mm, I'm setting. Why am I setting first value to update the ring with the index of the descriptor chain and then increment the field index? So this is incremented value. But why 1? Shouldn't it be 0? Shouldn't it be 0? This is why I need more comments. Probably last time I had something in my mind and that came up pretty quickly, but right now I have no idea why there's a 1 here. But and which queue notify will notify the index within the ring? Let's read if we have any. We do have it. Select the queue, writing its index. Queue itself is just fine because queue currently this particular thing is just going to use q0 all the time, so I think we're not changing that part. Yes, and finally we write, so it does not matter. Only thing we need to make sure is of that we need the count and we need the current indices that are in use, and after that we should be able to, I think, nothing much. Yeah, let's try it once, and then if we get blocked by something, we'll know what else is missing. Right now, on top of my mind, nothing else comes up. I believe only this variable is needs to be dynamic. And what else is hard coded? Yeah, the next variable is hard coded. This also needs to be updated properly. Ring. Now I guess I need to understand this because I think this will be an issue in quite a it's in near future, because this one feels like a hard coded value and I'm pretty sure this needs to be updated. I think it's the first request. And for right, yeah, see, This is the 0th request and that's the first request. I just remembered it. Because in our case, read and write is the one that comes first. Because it says a static example, so write comes first. So it's the 0th request. So we are using the 0th index within the ring. And then we have the read request, so that's the second request. So we have the index 1 for it. So I think global count should be enough for this, because whichever whichever index is free, we use that index here. I think we need also a ring we need user requests info and used requests index. This will be of 24 and this will be of 12. This just gives the current count. So this is also up to 12. There's a difference between this and this, because counts can be just the incremented value, but index, because if we use one index 2 once and then we free up it in the middle of let's say after using 7 and 8, then we can still use 2 back again. That won't be possible if we have just count. So yeah, let's also have index. I think nothing much. Let's just write it. Block data. Yeah, block data. I don't know if it makes sense, but it's fine. It's gonna have one uint 8 count, global count, and it's gonna have a buffer, and it's also just uint 8 used request info, and it's gonna be of size 24 because there is 24 possible indices. And then we have the third one, which is uint64 used requests indices, and this is there's only 12 indices. And every time we can just go through this 12 index and find a new request. As long as the global count is less than 12, we can just go through it and find a new index. And once we have the new indices, okay, maybe we can just have a structure of if we have an index, let's say 2, that is free, that means the index 2, 3 and 4 should be free in request info 2. If we assume that, then we don't need this. Would that be good? I think it's not an issue, because if we have that proper assumption and we know that index 2 is free, then we only use index 2, 3 and 4 for the requests. And if someone else is using index 6, then they will know they'll only have to use 6, 7 and 8. I think we can go that way. Let's write it down. If index 0 is used, that means 0, 1, 2 is allocated. This will be assumed. Yeah. And if index 2 is index 1 is used, that means 3, 4 and 5 is allocated. Yeah, I think if we go this way, we don't have to keep track of this 24 values. Yeah, I guess it should be good. Let's try this. Let's put a type def then. Type def log data, and it's going to be log data. Okay, I guess it's good. Now we can allocate this in our init function, because that's the first thing that's gonna be called, that is init which.io backend. When this is called, we can just directly assume that we'll have a static block data star pointer, which is global block data. And it's going to be null. How do we set null? We set null. Just put here. And here we can let's assign it, and it's going to be global block data equal to block data star kmalloc size of block data. Perfect. Now we have the block data. Let's initialize it, and I guess we can write a helper for it. Whatever. Let's just put it here. It's going to be global block data dot global count equal to 0. Currently there's nothing. And global block data of request used index equal to zeros. No, this is already assigned, so I can just put I equal to 0. For int I equal to 0, I less than 12, I plus plus. And let's just set I equal to 0 just in case if someone else uses it. I think it's a local variable, so it's fine. Okay, perfect. Now we have set it to initialized it to Day-22. Now within the actual requests, within block reads, we need some helpers that can just get this current unused index. So we need a helper for it. So let's write one. It's gonna return an index, so that is uint 64, let's say. Find free index, and it's not gonna take anything. It's just gonna simply iterate over it. So it's just for uint 64 I equal to 0, I less than, we also have this max value because there can be only 12 requests maximum. Maximum of 12 requests. Plus. Okay, so what do? We if I is less than 12, then we have to check the index. Yeah, we go to global data dot used index of I. We check if this index is free. If this index equal to 0, that means it is free. If it's equal to 0, that means we can say printf index is free for usage. Okay, what else? Then we can just return we can return as soon as we find the first index. In case we don't find anything, then we return -1. Oh, okay, I can't use -1 here. Then I have to return I cannot return. I guess it would be nice to have int 64. That way I can just return -1 in case there isn't any index. It should be int 64, int 64, and if there's another thing there, we just return -1. If it's -1, the user just has to confirm if it is -1 or not. If it is -1, then they have to write their own while loop of waiting or do whatever they want to do. Okay, so we um, do that here. We put a while loop, while find free index int 64 free index equal to 0, free index equal to find free index. Then let me just start with -1, and as long as this is -1, as long as free index equal to -1, I simply keep on doing the same thing. Free index equal to this. I just keep calling the same thing. But at some point it has to get freed, and we'll get a free index, and the free index would be the uint 32 free index. Okay, now we find a free index and we use that to set those values, and then what do we do? Okay, let's write some stupid code. It's going to be free index and what this index has to be, it's a uint 16. So it's uint 16 free index plus 1. And this is u index plus 2. That's it. That is also dynamic now. Now this will be the global requests, current global. Yeah, that needs to be done. So if then I also have to update this as soon as I get a free. I have to set the global block data dot global count equal to plus equal to 1. This needs to be within a mutex, but currently I don't have that, so let's just put a to do here. We need to sync this, or maybe I can just use some atomic assembly to increment this. That should be doable because I can just take this, so it will always be atomic. I don't need an extra data structure to uh, keep it synchronous in the high level. Let's just put a to do. We need mutex something here before we increment this as someone else can also do it. Currently, I guess as per my scheduling, it is not possible because my scheduling will does not have threads and there is only one CPU and everything is time sliced. So I think it's just fine. But yeah, let's see. There's a race condition. Fuck me. If I, let's say, if I increment it and if I get descheduled here at this gap and someone else increments this, then if I try to read that value here, it's gonna fuck me up. This entire find free index should be within a mutex. That's the only possible way. Yeah, only then I can for sure say that I found it and I have a value and it's stored already and nobody else uh, were doing anything in between. Yeah, that's sad. That's fucking sad. Maybe we can just make this an atomic operation, but how can I make the entire thing atomic operation? That's not possible. No matter how I think about it, there will be a race condition there because if it gets scheduled off right before something, then there is a window where some other process can increment it. Fuck me. I think I have to write some sort of syncing mechanism. I don't want to write it now. let's just get this working first, and then we can think about it later. Mm, we have indices, we have length. This is the key because I have to use the global count here. Or what should I use here actually? I should use the free index. There's another issue. So the free index is actually supposed to return I into 3, because if it is 0, that means 0, 1, 2 is used. Then if it is index is 1, that means it should return 3, that is 3, 4, 5. And if it is index 2, then it should return 6, that is 6, 7, 8. Yeah, so let's put that into 3. Then I'll get a free index that I can actually use with this way. I can simply increment them, and also I can directly use the free index here. I don't even need the incremented global count. Yes, because it's just going to give the next possible index that is free, and I can use that index here. Yep, it should work. And I can use free index. Free index equal to 1. What is this? I think this is also the same thing that I have. So it's free index. And this needs to be incremented. Index plus equal to 1. Same thing, free index and free index. Okay, let's try it. Let's see if at least the read is working or not. I think read, let's just confirm it by writing something else. I don't, maybe it's just reading what was there before, we don't know that. So let's be 100% sure about it. It should be actually it did not write. Something failed. No, it worked. 72. Okay, so it is working. And what did we update? We updated the read operation, and read operation definitely worked. So let's also update the write operation now. We simply need this one step. And we can put it here. And we update this to, I guess previously we were just using the same operation. That's why it works. It's not good. That's not what we want. I think we were just, for both requests, we were updating the same index. Something like that. Because both things have the same next value. Okay, we have updated everything. Let's see what happens. Now we fucked up. We are stuck at status bits. Where is status bits? Looped descriptor. Okay, it's saying something like I have looped a descriptor. Maybe free index plus 1. It should be free index whichever value that comes here. And free index plus 2. And inside the ring we put the free index, which is the index that we want to use, and we increment the value, notify the queue, and the status bit is the one where we so did the write operation work? Looks like the write operation did succeed. Why did write operation succeed then? We starting to write here. We prepared the requests. Plus 2. Hopefully that's the issue. Well, I don't know. We'll see. Yep, that was the issue. I just simply did not, I copy pasted it, but I did not, because for the next descriptor it should be 2, right? That's why it said you have descriptor looped somewhere. Yeah. Okay, the moment has come. We can just simply try the same operation twice and see if it is working. We copy the entire thing and we paste it. And for the second attempt, we can remove the initializers and we can update the thing as J. Let's see. Okay, it works. Just to be sure, let's print it before that once. May print it here. Yep, we have 72 here and then we have 74. We have managed to finish this. So we have a high level API working that can be called as many as times. I guess we can call up to 12 requests. After that it will fucking fail. Let's try it. And in the last attempt, let's put one new. And let's put one more. Let's put one R. Let's try 85, 79, 82, and 74. Okay, everything is working. Because right now everything is sequential, so it should work. Yeah. And we don't need that many examples. Let's just keep it down to the 2 operations that we tried. So we have okay, right now we only have 1, then let's just paste once. Yeah, so we have 2 operations now. If we try it. Okay, it's all good. I think we have a good implementation of it. Is our batching works because we have writes and test that works, and we need to group the writes and read into a high level API. I think this is what is the high level API. And we can pass the data and how many bytes to write. Everything's fine. And the batch request is just that it needs to be sent dynamically, and we have updated the indices properly, so it can be sent as many as times we want. There's no limitation at this point, as long as it's under 12 requests. If it's more than 12 requests, what will happen? Some requests has to be finished, and then Until then, we'll stop in that while loop and it will keep on returning -1. Yeah. I think that's it. We managed to get it working. This is also working. Multiple requests are working now. Okay. So what do we need now? We have the block read and block write. Do we need anything else in block layer? Mm, I don't think we need anything else. We have the block layer in general should give read and write to a sector. That's it. Nothing much. Now it's the file system layers and work to keep track of sectors and stuff. So it's not our job. We have it fine. I think now it's time to rewrite some syncing mechanism. We need to look into how ARM gives any. Is there any specific ARM instruction that we can use to create syncing, atomic syncing, stuff like that? Let's just go through it and see. Let's write it down. Now let's think about writing one atomic mutex kind of data structure. So the high level operations can be synced between two processes as they all gonna be racing eventually. Do this before we get into the VFS implementation. Yeah, I think that would be a good thing to first of all finish. But right now, today we managed to make our existing implementation, which was a bit hard coded. It was only able to make 2 requests, and the indices were hard coded. Currently, we have added a new data structure that can keep track of the request that is currently being used. And if a request has a certain index, then the rest of the upcoming 3 indices will be used too. And we have this data structure, and that can help us to keep track of all the indices that are currently in use, and we can we can free them out. Fuck me, I didn't write the part where after the request is done, I did not free it. Yes, I just remembered it. After a request is done, we need to set the index as freed. Do this first. Yeah, maybe we'll just finish today. We still have time, 20 minutes. Yeah, I think it's not that big. We simply have to set global index of global used index of that free index equal to 0. Nothing much. Wait. I did not even set it to free here. I mean, I did not even set it to used here. Maybe I was just using the same index again and again. Ah, fuck, that's even worse. Let's set it to what, 1? And then we have to try it. Only then we can say that okay, it is working, but let's double check it. Now I have questions. Did I undo everything? Ah, fuck me. Redo. Let's see what happens. New index is 12 and then it is keep on waiting. Yeah. So I guess it is now working. Now let's just do one more thing. Let's just at the end of all operations we can set the index to 0 here. We set the free index equal to 0. And then these operations should also be synced, because this is in my setup it will work, but this is we need some sort of syncing mechanism for sure. But right now it is working fine, because we are not gonna use new index 15. Wait, let's print. Let's also print free index. Now we'll know what is what. Free index is 0. See, we keep just using the 0th index because our operations are almost sequential, because we have time slice, and within the time slice this entire thing is getting over. So once the operation is over, we are gonna set it to 0. But the real use case is not this, because we are not gonna simply call this sequentially in a k-main. This is going to be called from user space, and user space are going to be actually switched between. So when there is a write, there is someone else at the same time who can call read. So at that time we'll actually need the indices to work. To test that theory, that's why we have this if we don't set this to 0, it will never be freed, and we can keep using the upcoming bytes to just to be sure that we are able to use the upcoming bytes, and it was possible. So I think everything else is good. We'll have to test this from user space, but for sure. Yeah, let's write it down. To test parallel use of block read and write from user space. Currently we only tested it sequentially. Okay, that's it. Yeah, let's see. So we managed to at least get something working. We are able to dynamically send requests without having to hard code any indices, and we also tested it a little bit, and it is working. We also tried to exhaust the index limit, and we did see that we were stuck after 12 requests. So that point is also good, and we also have noted that we need to test it from user space, so that we also can see the parallel access instead of just sequential access. Other than that, yeah, nothing much. I guess, yeah, tomorrow we'll start thinking about the VFS layer, how to meddle with it and stuff like that. And tomorrow we first have to start with the syncing stuff. We need a data structure for it, and it needs to be properly synced, because before getting into user space we need to get that working and update them in all these parts. Yeah, nothing much. Thank you guys. Bye bye.